Hello everyone, myself Deepak Upadhyay from Impulse Technology, Gurgaon, Delhi. Today I will show you how to calculate the spin polarized quantum transport property of Zigzag graphene nanoribbons by using NanoDCAL software. So let's get started. This is my device studio, that is a graphical user interface for this NanoDCAL software that will help you to model the structure. You can do some modification, manipulation in your atomic structure, device structure as well. So first of all, I would like to click on the file option, and in the file option you can see this is for creating the new project. You can open your existing project, you can save your project, you can design your new device structure, crystal structure, molecule structure, and this is the import option. This software have two options to import the material. Either you can import the material from local database that exists inside this software, either you can import the material from online database. So this is the import option. This is the import local. Here you can see 0D material, 2D material, 1D material, 3D material, and some organic material is there. In 0D material, some molecule, amorphous and crystalline is there. This is the 1D material, some nanotube, different combination of crawl vectors, and this is the 2D material. This is the 2D material where you can see some novelty material, arsenic, bismuth, black phosphorus, and this is the graphene. This is the 3D material where you can see conductor, insulator, layer material, magnetic material, metal oxide, novelty material, and semiconductor material is there. This is the conductor, pure metals. This is the insulator. This is the layer material, magnetic material, metal oxide, novelty material, some perovskite, topological insulator. This is the perovskite. This is the topological insulator, semiconductor, and this is the organic material, some crystal and molecule is there. So the conclusion is all about that. This is the material database that exists inside this software. So to create a graphene nanoribbons, I would like to click on the build option, and in the build option you can see multiple options are there. So you can design your structure as per your need. So I would like to click on the graphene nanoribbons, and this is the graphene nanoribbons builder. Here you can see default carbon atom is selected, and if you want to change, double click on the carbon and periodic table will open. And from the periodic table option you can select any atoms as per your need. So also you can select the bond length, you can passivate with hydrogen atoms, and this is the crawl vector and an m value. So I have selected 2 by 2, and I would like to click on the preview option, and here you can see this is the zigzag graphene nanoribbons. I would like to click on the build option. This is the project window where input and output file will be shown, and this is the property window where the property of our whole structure will be shown, and this is the job manager. You can see this structure is quite thin, so it is better to increase the length. So I would like to click on the build option, and I would like to click on the redefine crystal. So I would like to increase the length 15 times in the direction of C, and then I would like to click on the preview option, and here you can see the length of this graphene nanoribbon has been increased. So I would like to click on the build option. So this is the 2 by 2 zigzag graphene nanoribbon structure. So to make a device structure, I would like to click on the convert to device option. You can define left electrode, right electrode, bottom electrode, top electrode, front electrode, back electrode. In this structure only 2 electrode is possible, left and right. So I would like to select left electrode, right electrode, and here you can also change the electrode value as per your need. And I would like to click on the preview option. Here you can see electrode has been created. This is the left electrode, right electrode, and this is the center region. So I would like to click on the build option. To simulate this zigzag graphene nanoribbon structure, I would like to click on the simulator, select this NanoDCAL, and here you can choose the self-consistent field calculation. This is the self-consistent field calculation parameter. You can change electron temperature, cutoff energy, exchange correlation, LDA, GGA, K-point sampling. This is the contour integral. This is the electrode parameter where you can see left electrode, right electrode, and this is the iteration control, density matrix, Hamilton matrix, total energy, and this is the basic setting. And if you want to include some spin tonics application like collinear spin, general spin, so I would like to select collinear spin, and then I would like to click on this generate file. Once I click on this generate file, in the project window you can see the HCF input file device region, left electrode and right electrode has been generated. This is the HCF input file device, click on open with, and this is the script for this device region. Here you can see what parameter we have defined. This is the basic settings, description of electrode, and this is the contour integral, and I have selected collinear spin, and this is the iteration control, and this is the atom and their Cartesian coordinate point. So first you need to run this electrode parameters, and then you can run this center region. So I would like to click on the run option, and here you can define the number of parallel cores. Suppose if you want to run this job in parallel, suppose 5 core, 10 core, 15 core. In my computer 4 core is there, so there is no limitation of core. You can define up to 120 core rate easily. So I would like to click on run option to run this job. So you can run this SCF input for the right electrode as well, and then you can run this SCF input for the device region. So on the bottom of the page you can see this is the job manager, and this is the status of your project. So in the meantime you can select the transport properties. So I would like to click on the simulator NanoDCAL, and then I would like to click on the analysis. This is the transport property, this is the device parameter, and if you want to show the left electrode, this is the left electrode parameter. So here you can choose what parameter you want to define from this structure. So I would like to select density of state, total energy, scattering state, transmission, IV calculation, electron density, potential. This is the density of state parameter, K point sampling, number of energy point, energy range. This is the scattering state, and this is the transmission, K point sampling, number of energy point, energy range, and this is the IV calculation. Here you can click on this generate file, and once you click on this generate file, the analysis input file will be generated, and you can run all the analysis parameter as well. So in order to get the spin current as a function of voltage, we should perform the self-consistent field calculation considering different source voltage. In the SCF input you can see there is no voltage defined, so you can copy this project. So to get a spin current as a function of voltage, so we need to run this SCF input for the 0.2 voltage. So I would like to click on the simulator, go to the NanoDCAL, and here I would like to select this self-consistent field calculation, and here I would need to define the voltage point. Here you can see left electrode is 0 voltage and right electrode is 0.2 voltage, and then I would like to click on the generate file. This project is for the 0 biasing voltage, and this project is for the 0.2 voltage. Similarly you can run all this SCF input, and then also you can choose the analysis parameter, select this NanoDCAL, go to the analysis part, and here you can select this IV calculation, and then you can click on this generate file. So you need to run all this SCF input and IV input as well. Similarly you can copy this project, and this project is for the 0.24 voltage. So I would like to again click on the simulator, go to the NanoDCAL, click on the SCF input, and here I would like to define the voltage as 0.4, and here I would like to select this collinear spin as well, and then I would like to click on this generate file. So you can run all these input parameters, and then you can click on the simulator NanoDCAL, and then you can choose the analysis parameter, and here you can select this IV curve, and then you can click on this generate files. Again you can copy this project, and this is for the 0.6 voltage, and then you can click on the OK, and here you can see this project is for the 0.6 voltage. Again I would like to click on the simulator NanoDCAL, and then go to the SCF calculation. Here I would like to define the voltage 0.6, and then select the spin type collinear spin, and then I would like to click on this generate files, and again you need to run all this SCF input, and then you can click on the simulator NanoDCAL, and then you can choose the analysis, and here you can define the IV curve, and then you can click on this generate file. Again you can copy this project, and this project is for the 0.8 voltage, and then you can click on the OK. Again you can select this 0.8 voltage, go to the simulator NanoDCAL, and here you can select the SCF parameters, and here I would like to define the voltage 0.8 voltage, and again spin types collinear spin, and then I would like to click on this generate file. Again you need to run all this SCF input. First you can run this electrode, right electrode, and then you can run this SCF for the device, and then you can go to the simulator NanoDCAL, and here you can select this analysis parameters, select this IV curve, and then you can click on this generate file. Again you can copy this project, and this project is for the 1.0 voltage. Then you can click on the OK. You can select this 1.0 voltage and go to the simulator NanoDCAL, and here you can choose the SCF parameter. This is the electrode, and here you need to define the voltage 1.0, and also you can choose the spin type collinear spin, and then you can click on this generate file. Again you need to run all the SCF input, and then you can click on this SCF input for the device, and then again go to the simulator NanoDCAL, and here you can choose the analysis, select this IV curve and click on the generate files. You can run this IV curve input file as well. Once all this SCF input calculation will finish, their output will be generated, so you can wait until the calculation finished. In job manager you can see all this SCF input parameter, IV parameter has been finished and their output has been generated. So you can see this is the density of state. You can right click and click on the show view, and this is the density of state with respect to energy. Here you can see this is the spin up, and if you want to show the spin down, this is the spin down, and this is the spin up and spin down graph. This is the transmission, spin up transmission, spin down transmission, and this is the both spin up and spin down, and this is the total transmission with respect to energy. This is the total electron density. This is the 3D model of this total electron density. If you want to show the 2D, this is the 2D view along x-axis, y-axis, z-axis, and this is the planar display. If you want to show the stereoscopic display, this is the stereoscopic display along z-axis, y-axis, x-axis, and this is the 1D view along xy plane, yz plane, xz plane. So 3D, 2D, 1D view is also possible. This is the Zigzag coefficient. This is the Zigzag coefficient along temperature, and if you want to show the chemical potential energy, this is the Zigzag coefficient along with the chemical potential energy. This is the exchange correlation. This is the exchange correlation of this graphene nanoribbon structure. This is the 3D view, and if you want to show the 2D, this is the 2D along x-axis, y-axis, z-axis. This is the planar display. If you want to show the stereoscopic display, this is the stereoscopic display along z-axis, y-axis, x-axis, and this is the 1D view along xy plane, yz plane, xz plane, and this is the current voltage curve.xml file, and this file will open in the Matlab. So I would like to open my Matlab. This is the Matlab. Here you can relocate your project. Here you can enter the location of your project, and this is the location of my project, and you can click on the enter. Here you can see this is the project and their output file. This is the 0.2 voltage, 0.4 voltage, 0.6 voltage, 0.8 voltage, and 1.0 voltage. So you can click on this device, and here you can see this is the Matlab file. So you can select this current voltage curve.mat file. Here you need to type the data. You can see voltage is 0 and current is minus 1.5078 into 10 to the power minus 5. Here you can see this is the voltage as 0.2 and this is the current 1.5078 into 10 to the power minus 5. Here you can click on this data. Once you click on this data, this interface will open, and here you can see V1 is 0, I1 is minus 1.5078 into 10 to the power minus 5, and this is the spin up and spin down current, and this is the V2 0.2 voltage, and this is the I2 1.5078 into 10 to the power minus 5, and this is the I2 spin up and spin down current. Again you can select this 0.4 voltage, and here you can select this device and double click on this current voltage curve.mat file, and here you need to type the data. Enter V1 is 0, I1 is minus 1.7970 into 10 to the power minus 5, and this is the voltage V2 0.4 voltage, and this is the I2 1.7970 into 10 to the power minus 5. Here you can type the data dot I1 is spin decomposed, and you can click on the enter, and this is the value of spin up and this is the value of spin down. Again you can select this 0.6 voltage project. Here you can select this device, and again you can click on this current voltage curve.mat file. Here you need to type the data, enter, and here you can see V1 is 0, I1 is minus 1.6416 into 10 to the power minus 5, V2 is 0.6 voltage, and I2 is 1.6416 into 10 to the power minus 5. Again you need to type this script, and here you can see this is the value of spin up and spin down current. So all the output file you can show like that. And for the final graph you can click on this new script. Once you click on the new script, this interface will open, and here you need to write the script. First I would like to comment output of spin current, and here I would like to define the voltage V1 equal bracket V2 equal bracket, and in the bracket you can define the output of this voltage V1 V2 I1 I2. In the V1 you can enter the voltage value 0, 0.2, 0.4, 0.6, 0.8 and 1.0. And in the I1 you can see, you can copy this I1 value, and here you need to paste. This is the value of I1. Once you enter all the value of voltage V1, V2, current I1, I2, you need to write this script for the plotting this IV calculation. And here you can see I have defined voltage at x-axis and I have defined the current at y-axis. Then I need to click on the run option. Once the calculation finished, this spin current will be generated. And here you can see this is the spin current for various supply devices voltage 0.2, 0.4, 0.6 and 1. And you can see this is the final graph of the spin current for the various supply devices voltage. So thank you for watching this video.